Dark matter's influence on cosmic structure. Dark matter comprises approximately 85% of the universe's total mass, creating an enormous three-dimensional network that spans the entire observable universe. This invisible substance interacts with ordinary matter only through gravitational attraction, yet it controls where every star and galaxy can exist throughout the cosmos. The cosmic architecture formed by dark matter determines precisely where light sources can form and how their illumination propagates through space. The gravitational influence of dark matter shapes cosmic structure through a process that began shortly after the Big Bang, when tiny density fluctuations in the primordial universe began growing under gravitational attraction. Dark matter particles, being immune to electromagnetic forces, could collapse into increasingly dense concentrations while ordinary matter remained dispersed in hot plasma. These early dark matter condensations created gravitational wells that eventually attracted gas and dust, providing the seeds around which the first stars and galaxies would later form. Recent research has revealed the intricate details of how dark matter constructs the cosmic web through sophisticated computer simulations that track billions of particles across cosmic time. These calculations show that dark matter forms an interconnected network of filamentary structures spanning millions of light years, with dense nodes occurring at intersection points where multiple filaments converge. The cosmic web acts as a scaffolding that channels ordinary matter along predetermined pathways, concentrating star-forming material into specific locations while leaving vast regions nearly empty of luminous objects. These filamentary structures create enormous voids between galaxy clusters where virtually no stars exist to contribute illumination. The largest cosmic voids span hundreds of millions of light years in diameter, containing density levels less than 10% of the cosmic average. Within these supervoids, galaxy densities drop to nearly zero, creating regions of space where starlight sources become separated by distances so vast that their combined illumination cannot brighten the intervening darkness. Dark matter's gravitational clustering explains why visible matter concentrates into galaxies rather than spreading uniformly throughout space. Without dark matter's attractive influence, the ordinary matter that forms stars would remain evenly distributed across cosmic volumes, potentially creating the uniform stellar distribution that early astronomers assumed must exist. Instead, dark matter's gravitational effects gather star-forming material into dense concentrations, leaving enormous empty regions between these stellar accumulations. Studies of cosmic web formation have identified how dark matter creates what astronomers describe as a lumpy universe where matter distribution varies dramatically across different scales. Computer models tracking dark matter evolution show that gravitational instabilities amplify small initial density variations into the dramatic contrast observed today. Regions that began with slightly higher dark matter concentrations grew into massive galaxy clusters, while areas with lower initial densities became increasingly empty as material drained away toward denser regions. This cosmic lumpiness directly affects our perception of universe brightness by concentrating light sources into specific locations while creating vast dark zones between them. If dark matter distributed ordinary matter uniformly throughout space, every direction in the night sky would contain similar numbers of stars at various distances. Instead, dark matter's gravitational architecture creates dramatic variations in stellar density, with some directions showing rich galaxy clusters while others reveal nearly empty voids, stretching across hundreds of millions of light years. Gravitational lensing effects caused by dark matter concentrations further influence how starlight reaches Earth by bending and redirecting photon paths through curved space-time. Massive dark matter structures create gravitational fields strong enough to deflect light rays, causing distant galaxies to appear distorted, magnified, or displaced from their actual positions. These lensing effects can focus light from background sources, making some objects appear brighter than expected, while simultaneously creating shadow zones where light gets deflected away from potential observers. Large-scale surveys mapping dark matter distribution have revealed how this invisible architecture creates systematic patterns in cosmic illumination. Cosmic web surveys show that approximately 50% of cosmic volume consists of voids containing less than 20% of average matter density. These underdense regions contribute minimal starlight to the cosmic background, while the remaining matter concentrates into filaments and nodes that produce bright but isolated sources of illumination. Dark matter's influence extends to individual galaxy formation processes that determine how efficiently ordinary matter converts into luminous stars. The gravitational potential wells created by dark matter halos control how gas flows into galaxies and regulate star formation rates through complex feedback mechanisms. Galaxies forming within more massive dark matter halos tend to contain larger stellar populations, while those in smaller halos remain dim or fail to form stars altogether. The cosmic web structure ensures that most of space remains permanently dark by preventing uniform star distribution across cosmic volumes. Dark matter filaments channel star, forming material along specific pathways, creating highways of galaxy formation that connect dense nodes while bypassing enormous empty regions. This channeling effect concentrates available luminous matter into narrow corridors, leaving the majority of cosmic volume virtually devoid of light sources. Computer simulations tracking cosmic evolution over billions of years show that dark matter's architectural influence strengthens over time as gravitational clustering continues. The contrast between dense and empty regions increases as matter continues flowing from voids into filaments and nodes. This ongoing concentration process creates an increasingly sparse network where luminous objects cluster into isolated regions separated by vast empty zones, maintaining the characteristic darkness that dominates the universal environment. Yet this current cosmic architecture represents only a snapshot of an evolving system whose illumination patterns will undergo dramatic changes as the universe continues aging through deep time. The future of cosmic darkness. These evolutionary timelines reveal the universe's inevitable trajectory toward complete darkness. Rather than growing brighter over time, space faces an inescapable march toward eternal night. Every star currently illuminating the cosmos represents a temporary beacon that will eventually exhaust its nuclear fuel and fade into obscurity, leaving behind only cold remnants scattered throughout an ever-expanding void.